Good morning. Hello everyone. Welcome to my course Basic Electronics Engineering. This course is generally made for BTech degree students of second year. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Baraipur, a college under JIS Group Educational Initiatives. Students, you can personally meet me at college premises, ground floor physics lab, or you can also send me a mail regarding your query and doubts to my given mail address, that is godphysics6@gmail.com or gopal.chakraborty_gkcem@jisgroup.org. Students, I have a YouTube channel. The link is given here. You can follow my YouTube page for more videos as per your markout syllabus. And if you feel any doubt or any query, feel free to contact me. The corresponding course pages are www.markoutexam.net and www.markoutwb.ac.in. The syllabus is already uploaded in the university website. The link is given here. If you want, you can download the syllabus from the given link. The title of the course is Basic Electronics Engineering. Subject code is ES-ECE 301. It is under the category of Engineering Science course. It has a credit 3 lecture per week. This subject has no practicals. This subject is generally made for BTech degree students of second year, third semester. So, apart from all other departments, only the student of mechanical engineering department has to study this subject for the part of their curriculum of second year, third semester. So, but for this subject, I am your subject teacher. The topic that I will going to be discuss in today's class is basics of op-amp based adder and subtractor and op-amp based differentiator and integrator circuit. Prerequisite for this Topic is idea of semiconductor physics. This topic is also under module 1, that is semiconductor device and its applications. So as far as I have discussed the details in modules 1, this topic is also under module 2, that is operational amplifier and its applications. The course objective is to provide an overview of basics of op-amp based adder and subtractor, and op-amp based differentiator and integrator. After completion of this course, students will able to understand the principles of op-amp based adder and subtractor and op-amp based differentiator and integrator circuits. So, before going to start with today's topic, I would like to remind you that I have already uploaded 2 or 3 videos on this module 2, that is operational amplifier. So in this module I have already discussed about the basics of operational amplifier and also the construction of operational amplifier. So students, you have to go through that video class lessons to understand this today's class, because in today's class I will going to discuss some applications of using op-amp circuit. So that is that I have already told you in that previous class that using op-amp you will able to some arithmetic operations can be solved. Now these arithmetic operations can be addition, can be subtraction, can be follower, can be differentiating, can be integration, and lots of other arithmetic operation can also be solved by operational amplifier or op-amp. Now in today's class I am going to discuss the arithmetic operation based on op-amp, that is adder, subtractor, differentiator and integrator. So to understand today's class you need to know the basics of op-amp. So for this I like to request you to go through that previous video class lessons, so it will be very helpful for you to understand today's class. What we have seen in case of op-amp based inverting amplifier and non-inverting amplifier, that op-amp has 2 input. One is inverting input, another one is non-inverting input, and only a single output. So in case of inverting amplifier, we have to apply the voltage at inverting terminal. At the same time, we have to ground the non-inverting terminal. So what we have found at the output, the phase will be changed of 180 degree, and the overall gain of the op-amp is minus of RF by R1. That means feedback resistance by input resistance. And in case of non-inverting amplifier, we have to apply the input voltages at the non-inverting terminal. At the same time, we have to ground the inverting one. So what we have found, the overall voltage gain, that is equals to output voltage by input voltage, that's equals to 1 plus RF by R1. So it means in case of non-inverting amplifier, the overall gain will be greater than 1, and also output will be in the same phase with the input. So these are the basics of inverting and non-inverting amplifier based on op-amp. So the basic idea of the circuit connection is almost same also for adder and subtractor, but you need to clear your idea for inverting and non-inverting amplifier before going further with the adder and subtractor. So now I am going to discuss all these 4 operations of using op-amp one by one. So the arithmetic circuit. In the previous chapter we discussed about the basic applications of op-amp. Note that they come under the linear operations of an op-amp. In this chapter, let us discuss about arithmetic circuit, which are also linear applications of op-amp. The electronic circuit which perform arithmetic operations are called as arithmetic circuit. Using op-amp, you can build basic arithmetic circuit such as an adder and a subtractor. So one by one I will discuss with the circuit. An adder is an electronic circuit that produces an output which is equal to the sum of the applied input. So in this section discuss about the op-amp based on adder circuit. An op-amp based adder produces an output equal to the sum of input voltages applied at its inverting terminal. It is also called a summing amplifier since the output is an amplified one. So this is the circuit describe the op-amp based adder. You can see in this circuit here, this is the inverting input, inverting terminal of the op-amp, and this one is the non-inverting terminal, and this one is the output. So what we have done, we have applied two voltage. One is V1 and another one is V2 through resistance R1 and resistance R2 to the inverting input. So these voltage are applied in the same point, same input. At the same time, we have ground the non-inverting terminal of the op-amp, and here from the output voltage we have taken a feedback through a resistance RF. So this is the basic circuit diagram. Now in the above circuit, the non-inverting input terminal of the op-amp is connected to ground. That means 0 volt is applied at its non-inverting input terminal. According to the virtual short concept, the voltage at the inverting input terminal of an op-amp is same as that of the voltage at its non-inverting input terminal. So the voltage at the inverting input terminal of the op-amp will be 0 volt. Now, as per nodal equation, at the inverting input terminal node, we can write 0 minus V1 by R1, that is the current through the resistance R1, plus 0 minus V2 by R2, that is the current through resistance R2, plus 0 minus V0 by RF, that is the current through RF. That's equals to 0. So rearranging, we get V1 by R1 minus V2 by R2, that is equals to V0 by RF. So we get V0 equals to RF into V1 by R1 plus V2 by R2. Now, if RF is equals to R1 equals to R2 is equals to R, so R will be cancelled out. So you will get V0 is equals to minus of V1 plus V2. So therefore, op-amp based adder circuit discussed above will produce the sum of two input voltages V1 and V2 as the output when all the resistors present in the circuit are at the same value. Note that the output voltage V0 of an adder circuit is having a negative sign, which indicates that there exists a 180-degree phase shift between input and output terminals. Second one, a subtractor. Subtractor is an electronic circuit that produces an output which is equal to the difference of the applied input. This section discusses the op-amp subtractor circuit. An op-amp based subtractor produces an output equal to the difference of the input voltages applied at its inverting and non-inverting terminals. It is also called a difference amplifier. Since the output is an amplified one, the circuit diagram is shown here. Here, the procedure is very simple. We have applied V1 through resistance R2 in the non-inverting terminal and R3 with the ground, and voltage V2 through resistance R1 in the inverting terminal, and there is a feedback resistance with the output. Now, in this case, we will simply calculate the output voltage considering only the V1, then the output voltage considering only the V2. After calculating separately the output voltage for V1 and V2, we will just sum up these two. We will give you the total output voltage for this input voltage V1 and V2. This is the basic procedure. So firstly, let us calculate the output voltage V01 by considering only V1. For these, eliminate V2 by making this circuit. We obtain the modified circuit diagram as shown in the figure. So here we have make V2 ground. Now using voltage division principle, calculate the voltage at the non-inverting input terminal of the op-amp. And what we find? That Vp, that is equals to V1 whole into R3 by R2 plus R3. Now the above circuit looks like a non-inverting amplifier having input voltage Vp. So therefore the output voltage V01 of the circuit will be V01 is equals to Vp whole into 1 plus R by R1. Now subtracting that value Vp in the above equation, we get V01 is equals to V1 whole into R3 by R2 plus R3 into whole into 1 plus R by R1. Step 2. In this step, let us find the output voltage V02 by considering only V2. Similar to that above step, eliminate V1 by making it short circuit. So we have make this grounded. So you can observe that the voltage at the non-inverting input terminal of the op-amp will be 0. It means the above circuit is simply an inverting op-amp. So V02 will be whole into minus R by R1 into V2. Now we have to add this V01 and V02 to get the output voltage. So V0 equals to V01 plus V02. Now substituting the value, we get V0 equals to V1 whole into R3 by R2 plus R3 whole into 1 plus R by R1 minus R by R1 into V2. Now putting all the resistance equal, that is equals to R, we will get V0 equals to V1 whole into R by R plus R whole into 1 plus R by R minus R by R into V2. So calculating, we get V0 equals to V1 minus V2. So the op-amp is here using base subtractor circuit discussed above will produce an output which is the difference of two input V1 and V2 when all resistor present in the circuit are the same value. Now differentiator and integrator. And differentiator is an electronic circuit that produces an output equal to the first derivative of the input. Here the circuit is given below. So what we have done, here the input, we have put an input Vi at the inverting terminal through a capacitor. The non-inverting terminal is grounded and there is a feedback resistance, that is R. So an op-amp based on the differentiator produces an output which is equals to the differential of the input voltage that is applied to its inverting terminal. The circuit diagram of the op-amp based differentiator shows here. In this circuit, the non-inverting input terminal Now, according to the virtual short concept, the voltage at the inverting input terminal of the op-amp will be equal to the voltage present at its non-inverting input terminal. So the voltage at the inverting input terminal of the op-amp will be 0. The nodal equation at this point inverting input terminals is C d of 0 minus Vi by dt plus 0 minus V0 by R equals to 0 minus C dVi by dt equals to V0 by R. So V0 equals to minus RC dVi dt. If RC equals to 1 second, then the output voltage V0 will be minus dVi dt. Thus the op-amp based differential circuit shown above will produce an output which is differential of the input voltage Vi. And the negative sign that indicates there is a 180-degree phase difference between input and output. Next one, that is integrator. And an integrator is an electronic circuit that produces an output that is the integration of the applied input. Now an op-amp-based integrator produces an output which is an integral of the input voltage applied to its inverting terminal. Now I will show you the circuit diagram. So this is an integrator circuit. So only the change with the differentiator circuit is that we have replaced the feedback resistance with the capacitor and capacitor by the resistance. So here we have applied the input voltage through a resistance R at the inverting terminal, and we have considered a feedback with the capacitance C. So in this circuit, the non-inverting input terminal of the op-amp is connected to ground. That means 0 volt is applied to its non-inverting input terminal. So as per virtual short concept, the voltage at the inverting input terminal of the op-amp will be equal to the voltage present at its non-inverting input terminal. So the voltage at the inverting input terminal of the op-amp will be 0 volt. Again we have to apply the nodal equation at the inverting input terminal gives 0 minus Vi by R plus C d of 0 minus V0 by dt equals to 0. So rearranging we get dV0 dt equals to minus of Vi by RC, or dV0 equals to minus of Vi by RC dt. So integrating both sides we get V0 equals to minus of 1 by RC integration Vi dt. If RC equals to 1 second, then the output voltage V0 will be equals to minus of integration of Vi dt. So the op-amp based integrated circuit discussed above will produce an output which is the integral of the input voltage Vi when the magnitude of impedances of the resistor and capacitor are reciprocal to each other, and the negative sign indicates that the output is 180 degree out of phase with the input. These are the reference book that you can refer. The evaluation process is same. Students have to appear for 70 marks in semester exam and 30 marks in internal exam, out of which 15 marks for examination, 10 marks for assignment, and 5 marks for attendance. Hope all of you have understand and enjoyed today's class. In next class, I will discuss the converter. So, thank you.